So welcome back again to Lesson 3 on how the history of thinking about speleogenesis or cave forming has evolved. And we left right at the start of the classic period back in the 1930s. Oscar Meinzer had gotten people thinking about whether water tables, whether dissolving of rock and corrosion by CO2 happened above the water table, at the water table, or below the water table. And that's really the big question, and in fact we still have modern day discussions about that. And I'm going to take us into some people that had, let me take you into some of the different ideas. I've got some slides up, and I'm going to start with the deep phreatic, the people that talked about things that happen below the water table. And the first one of those I want to talk about is a gentleman named William M. Davis. And working in about 1930, working throughout the 30s, but some publications in 1930, he started connecting the formation of caves or the origin of a cave to an erosion model. He did, it was already late in his career, he had started in the late 1800s with some of the other people who talked about rivers cutting down and landscapes being uplifted by plate tectonics, and that causing water to cut through the landscape and form caves because it had that erosional capacity. And so he emphasized that that actually could also happen deep below the water table, and then the caves could be lifted up to where we would get in them. And all of those then fit very well with modern geology thinking at the time, that geology covers vast amounts of time, hundreds of millions or billions of years. And so when you have long time passages like that, it only takes small incremental changes to make something like a cave. The next one I want to talk about with that deep phreatic thought is a guy named Harlen Bretz. And he's very well known here in Missouri and in fact many places in the world. He was a geology professor at, I believe, the University of Chicago. And he came up with a lot of different theories. He studied a lot of the caves in Missouri. In fact, he studied so many he created a book called Caves of Missouri. And in that he talked about a number of the caves that he had crawled through, and any of the local cavers will tell you he was spot on when he said they're all full of unctuous red mud. It's red clay that's very sticky. But what he really did as a scientist was to distinguish between the phreatic features, the things that were formed by flowing underneath the water table, and the vadose features, the things that were formed above the water table as water would soak through. And he said, in his theory, the caves formed underneath the water table, and then later, after the water table dropped or the landscape rose up, the caves were modified by vadose waters. And if you think about that, that is sort of a modern concept, that we have caves and then they have stalactites and stalagmites. Most of our modern scientists would say those formed at separate times. The cave passage became a hollow or a void before crystals could start dripping through or something could start dripping through the roof. And so he had that concept. He talked about there would even be a stagnant phase in between the water table rising or forming below the water table and then the water table dropping, where the cave would actually fill up with sediments as the water table dropped, and then even that would have the vadose water maybe flowing through it and removing those sediments later. Well, take his thought and the previous other deep phreatic thought, and let's move and look at people that said, well, it doesn't really happen very deep in the rocks. That as water goes deeper in the rock, it already absorbs a lot of limestone. Anyone who's ever tried to dissolve sugar into sweetened iced tea knows that the more you have the same material dissolved into your liquid, the slower the process goes. And so there becomes a maximum capacity. And so some of the scientists said you can't do a lot of dissolving deep underground. It has to be shallower, very close to the water table. Some of the people that we're going to talk about that, there's a gentleman named Alan Swinnerton in the early 1930s. He said most of the passages he had seen, most of the cave passages, had what he called a low gradient, a fairly low slope. They're not steep, they were fairly level, almost level, and that must mean that they were forming about where the water table, which typically is fairly level, would have formed. There was another gentleman in the late 1930s, Dr. Malott, who said floodwater invades into caves, and that creates a lot more corrosion and erosion right around the level that the water floods in, which would again be the water table. And then in the early 1940s, a couple of scientists, Rhodes and Sinakori, published something that said they saw caves that were largest and most active right near the outlet, right near where the spring that runs the water out of the mouth of the cave exists, and that the cave grows larger headward, back in towards the start of the stream, and it does that over time. And a lot of people, I think, consider that maybe one of the first modern scientific consideration of how caves could actually not just form, but grow. And so we've gone from thinking above the water table, below the water table, at the water table, to having some people kind of focus in on maybe a lot of stuff happens right at the water table, and maybe it even happens as floods occur, as the water table fluctuates up and down, and it might even start where the caves are the largest, where all the water comes together to go out the hillside into a spring, and it starts to grow back into the hillside, if you would. Well, as you might guess, that was in 1941 that they published it, and anyone who's good with American history knows that at the end of 1941, America entered World War II. There were wars in Europe, so a lot of the scientific discovery of nature tended to sort of sit behind, take a back seat to the World War effort. And so we're going to fast forward to the 1950s. And starting in the 1950s, a gentleman named Clifford Kay published a document, a report that said he looked at solvent motion on limestone solution. He actually did some experiments where he took blocks of carbonate rocks, limestones, and shot jets of acid onto that and measured how fast the limestone would dissolve. And he could actually correlate the fluid flow, the speed of the water, to how fast the carbonate rocks, the limestone, dissolved. So that got people back into thinking of these new ideas, and I'm going to kind of move a little quicker here. We jumped into the 1960s then as people jumped into this, and someone figured out how to use tracer dyes, photochemical dyes, much like you might put food coloring in a glass of water and notice it kind of swirling throughout the water. We use certain designer dyes, and we could use those to trace groundwater. And so people, even in the 1960s, started this concept, and that gave us immense information on how drainage basins form, what sinkholes were connected to a stream going through a cave, to a spring, to an outlet. And in fact, some of that work connected many caves that people previously thought were independent of one another because the water just kind of went through a passage that was too small to continue exploring, but now we could connect it because the water was traceable from one cave to another. And that gave us the use of a thing called hydrology, the study of how water moves. And that gave us a whole new classification system for caves. We could look at caves that were formed by limestone dissolving. We could look at caves that were formed by sulfuric acid dissolving or hydrothermal hot waters rising. And we could even look at things that were caves but not necessarily karst. Some people call them pseudokarst, some people call them karst-like caves. Those would be caves that are formed in ice, like glaciers or the ice sheets. Lava tube caves formed like in Hawaii, where the lava cools and solidifies on the land surface, but it flows underneath still. And so we could look at the shape of the cave passage, the pattern of them, whether they were branches like the dendritic network of a tree, or whether they were blocky boxes or following joints or cracks in the rock like a set of city streets on a grid. We could look at fossils in the walls or the types of rock themselves in the cave and talk about whether that type of rock dissolved faster or slower. And we could look at the sediments left behind in a cave and talk about whether those represented certain changes in water chemistry. And in fact, all of that got us to think about chemistry of the water along with the flow of the water. One of the modern leaders in cave thinking is a gentleman named William B. White. He recently retired from Penn State University after, I believe, close to 40 years there, and he has published widely in cave systems and has mentored many PhD students there. I put a quote on your slides that concerned with the actual mechanisms by which cracks and bedding planes and the layers in the rock enlarge into caves has become marking the beginning of a modern scientific era. So we've kind of moved from the classical era to modern thinking from about 1957 until today. And it's all about not just the water, but the rock type and the chemistry. I put on your slide how limestone dissolves, and we'll talk about that in a different session. But it's really just taking calcium carbonate, which is the mineral making up limestone, and water and carbon dioxide, and that gives you carbonic acid, and you can dissolve the rock away with that. And that causes most of our caves, I say most because sometimes we have sulfuric acid or some other type of chemicals in there that would give us a different type of cave. And that would be something that we've also been able to track, hydrothermal caves where the hot water is pushing upward rather than cold water dropping downward. And it also lets us look at things that dissolve faster or slower in sulfuric acid than they do in carbonic acid. And then in the late 1960s, there was another professor, John Threlkill, at the University of Kentucky, who published an article where he started approaching the chemistry. And because by the 1960s we had campus mainframe computers that are probably less powerful than my watch is today, but they were strong enough to at least start doing some simulations. And so Dr. Threlkill did a nice job of combining the chemistry with computer models for how the rock dissolves and the speed at which it could dissolve, to follow up on all the way back Clifford Kay's work on shooting acid at the blocks and measuring how it dissolves. So now we have the ability to not only do lab experiments and measure things, but to actually do chemistry calculations on computers and hydraulics calculations for the hydrology of how water moves. And you put these together and we come back then to a figure I showed you in our last session. It's created by Derek Ford, who also started working in the late 1960s but is still currently active in the profession today, where he said you can form caves almost anywhere. You can form them underneath the water table if you have the right chemistry and temperature changes and gas changes in the water, and that fits with some of Threlkill's simulations. You can form them where the water is percolating through the vadose zone still, above the water table, but as it's moving through cracks and fractures, rainwater has enough carbon dioxide in it from the atmosphere to continue dissolving things. And you can especially form caves at the water table, it turns out. I haven't gone into the chemistry enough here today, but one of the key things we learned with the water chemistry is that if you mix two different waters, even though they both have a lot of calcite or limestone dissolved in them, just like mixing two big glasses of iced tea, if you've got all the sugar that each one can hold, it turns out if you mix them, you can still dissolve a little bit more in there. And that is what happens sometimes at the water table. The deep water and shallow water percolating in from the vadose zone mix and intermingle, and that allows more erosion and corrosion and dissolving right there at the water table. So just to quickly summarize the history of speleogenesis thinking, we go way back into the 1700s with some of the classic geologists, the first people to study the Earth, and they started looking at erosion and catastrophes and floods, and they worked their way backwards from catastrophic events to ongoing, long-term, small incremental geologic changes that happen over millions of years and thousands of years. And then that brought us to people who were thinking about water dissolving the rock either above the water table, below the water table, or at the water table. And that brought us into sort of the modern days with Meinzer and Bretz, Clifford Kay, John Threlkill, Derek Ford, Art Palmer, one of the books we've recommended for you, and Will White. And what all of those people started doing is the modern thinking is that we have to think about the geology, how the rocks influence the caves. We also have to think about the hydrology, how the water moves through those rocks, how it's moving to a base level or to a lower level drainage system of a main stream, a main stem like the Mississippi. And in between those two things, we also think about the chemistry itself, the actual processes and mechanisms by which the water and the rock interact and dissolve. So that's the second part of this first bit of lesson 3, and we'll get back to you soon with some more fun stuff. Thanks.